Hello students, it's Dr. Sansom, and today I want to talk about real gases. That is, gases that do not follow all of the assumptions of kinetic molecular theory. In particular, real gases have attractive forces between particles, and the size of the particles themselves is significant or non-negligible. In class, I showed you a graph where we had increasing pressure going from about 1 atmosphere to about 200 atmospheres, and we had a line here that represented how an ideal gas would behave. On the y-axis, we were plotting the real volume, or the observed volume, over what would be predicted by the ideal gas law. And we saw two different kinds of deviations from this line. The first kind is a dip below the line at lower to medium pressures, and the second kind is an increase above the line at very high pressures. The reason that these two deviations from the ideal gas behavior exist are because of the attractive forces between the particles and the size of the particles themselves. In this region where we have this dip below the line, the actual volume that we measure is smaller than the volume that we predict using the ideal gas law. And this happens because as we get to slightly higher pressures, the molecules are more likely to collide. So they are attracted to each other, and this causes the gas to contract a little bit. At these low to medium pressures, they're still far enough apart that the size of the particles isn't making too much of a difference, but the attractive forces are. And then when we get to this deviation above the line, this is when the observed volume is actually larger than what would be predicted by the ideal gas law. And this happens at very high pressures because the molecules are already so close together that in effect, the molecules themselves decrease the size of the container. So a larger container is needed to accommodate those molecules at that high pressure. In other words, the size of the molecules can't be neglected. Let's say we're looking at three gases, H2, O2, and CO2. Looking at these three gases, hydrogen has almost no attraction between particles. There's a little bit of London dispersion forces, but it actually doesn't show up here in this measurement at all. So I'll make a blue line for hydrogen. It would look something like this. It just goes up steadily because the size of the particles will always matter. And there's no decrease in the observed volume because of the attractive forces, because for hydrogen, those attractive forces are very weak. The black line that we have on here represents approximately what O2, or oxygen, would look like. This has some attractive forces. And CO2 will have even more attractive forces because it's a larger molecule. Oxygen molecules are medium-sized and the hydrogen molecules are small. So notice just looking at hydrogen and oxygen that hydrogen increases, but oxygen increases at a faster pace. The slope of the line that we see for oxygen is higher. That's because the size of the molecules is bigger. And if we look at CO2, I'll use a green line for CO2. CO2 is going to have an even deeper bend down here of attractive forces, but then, because it's larger, it's going to go up slightly more rapidly than oxygen did. So CO2 has more attraction, which gives it a bigger dip, but it's also the largest, which makes it increase more rapidly. I hope that is helpful. Happy studying.